Hey everyone, welcome to this explainer. Look, if you're stepping into data science, business analytics, or statistics, there's one predictive tool you absolutely have to master first, and that's regression analysis. It's basically the fundamental engine behind how we predict the future using data from the past. So today, we're going to break it down step by step.
Here is our roadmap for today. 1. What is regression? 2. Variables and visuals. 3. The math, best fit, and errors. 4. Types of models. 5. Real-world applications. And 6. A summary to lock it all in. Let's get right to it.
Section 1. What is regression? The intuitive core of prediction. So, at its intuitive core, regression analysis is a statistical method for defining the relationship between a dependent variable and one or more independent variables. Now, why do we actually do this? Well, to make predictions. Whether you're trying to forecast next month's product sales or maybe predict a patient's blood pressure based on their drug dosage, regression lets us mathematically quantify those relationships. It lets us evaluate the trends and forecast outcomes based entirely on historical data.
Section 2. Variables and visuals. Inputs, outputs, and scatterplots. All right, in any regression model, you're always dealing with inputs and outputs. The independent variables, which are plotted on the x-axis, are our inputs or predictors. These are the things we actually know, measure, or control. On the flip side, we have the dependent variable, which goes on the y-axis. This is our output or our target. It is literally the exact metric we are trying to predict or explain.
Let's actually see how these variables look in practice. Imagine a scatterplot for a business department. On our x-axis, we have the independent variable, the number of invoices they handle. On our y-axis, the dependent variable, the processing time in hours. Every single circle on the plot represents a historical record. Visually, we can instantly spot a directional relationship here, right? As the number of invoices goes up, the processing time generally goes up too.
But how do we turn a visual trend like that into a hard mathematical prediction? That brings us to Section 3, the math, best fit, and errors, formulas, and minimizing mistakes.
Okay, don't let the math scare you. This is the fundamental equation for simple linear regression. Y equals beta 0 plus beta 1 times x. Let's just break it down calmly. Y is the output we want to predict, and x is our known input. Beta 0, that's the intercept. It's exactly where the line crosses the y-axis when x is exactly 0. And beta 1 is our slope, which tells us precisely how much y changes for every single 1-unit increase in x. Put them together, and these parameters define the straight line that best fits our data.
When we plot that exact formula, we get our regression line. It represents our mathematical model, the algorithm's absolute best guess for predicting y given any x. But notice something crucial here. Almost none of the actual historical data points sit perfectly on that straight line.
That little imperfection is what we call residual error. A residual error is simply the vertical difference between an actual observed data point and the value predicted by a regression line. Because let's face it, in the real world, models are never 100% perfect. There's always going to be a gap between our straight line theory and the messy reality of what actually happened. So, to find the absolute best fitting line, we need to minimize those errors across the entire dataset. We do this using a cost function called mean squared error, or MSE. The formula here essentially averages the squared differences between the actual y values and our predicted y values. And we square those errors for a very specific reason. It stops positive and negative errors from just canceling each other out, and it heavily penalizes the really big mistakes.
So how does a machine learning algorithm actually find the line with the lowest MSE? It uses an optimization process like gradient descent. Here's how it flows. Step 1, it calculates the difference between actual and predicted values. Step 2, it squares those residuals. Step 3, it averages them to find the overall mean squared error. Finally, Step 4, it incrementally adjusts the slope and intercept of the line to make that MSE as tiny as possible. When that MSE hits rock bottom, boom, we've found our line of best fit.
Of course, the real world is rarely just a simple, straight-line relationship. Section 4. Types of models. Beyond a single straight line. Regression comes in a few variations, mostly depending on the shape and complexity of your data. We just covered simple linear regression, which uses one input to draw a straight line. But if you have multiple inputs, you graduate to multiple linear regression. If your data naturally curves, you'll apply polynomial regression, which fits a curved nth-degree line instead of a rigid one. And if you're trying to predict a binary outcome, like true or false, yes or no, you're going to use logistic regression.
To put that into a concrete comparison, agricultural scientists use multiple linear regression to predict crop yield based on the amount of fertilizer and the amount of water used. That's two independent inputs predicting one continuous output. Logistic regression, on the other hand, is built for probabilities. In business, you'd use it to predict a binary outcome, like whether a website visitor will click the buy button or just bounce off the page.
Knowing which model to apply is an absolute game changer. Section 5. Real-world applications, where data meets decisions.
The real-world utility of regression is just massive. In biopharma, portfolio managers use multiple regression to forecast sales and empirically quantify the exact return on investment for their marketing spend. Over in healthcare, researchers model how different dosages of a drug predictably impact a patient's blood pressure. And in general business, companies constantly rely on these models to predict their total sales volume based on their advertising budgets. It is literally the statistical backbone of evidence-based decision-making.
We've covered a lot of ground today. Section 6. Summary, key takeaways for data science beginners. If you're walking away from this explainer with anything today, make sure you lock in these 4 definitive takeaways. First, regression mathematically quantifies directional relationships between variables. Second, simple linear models rely on the core equation y equals beta 0 plus beta 1 times x. Third, finding the perfect model fit relies entirely on calculating and minimizing the mean squared error. And finally, when your data gets complex, you have to shift from simple lines to multiple, polynomial, or logistic variants.
I'll leave you with this final, somewhat provocative thought. If the entire foundation of regression is simply adjusting a mathematical model to minimize residual errors, how do you think these exact same principles of cost functions and gradient descent are powering today's most advanced machine learning and generative AI? It all starts right here with the fundamental math of minimizing mistakes. Keep exploring, keep learning, and I'll catch you in the next explainer.